Okay, welcome to the last session of the week. It's Friday morning, it's 9 a.m. We're all tired. I hope you had a good night yesterday. Let's take it easy, okay? So it's the idea is that you bring something home by doing things by yourself. Okay, so what I want to tell you today is something that goes into a little bit more details, thinking about what Professor Boglione told you in the past days. So these recitations are meant to be performed by pen and paper or chalk and blackboard. Okay, so I want to take a little bit of a different approach compared to what we did 2 days ago. I want to tell you something related to the QCD evolution equations and what their impact is, let's say, on the TMD parton distribution functions. So today we are going to discuss a little bit the predictive power of the formalism and the implementation of these evolution equations. So the predictive power is something that, okay, so what do you think is predictive power of a theory or, yeah, of a theory? Think about the words predictive power of a theory in general. What do you expect for that? Yes. Okay, that's yeah, goes in the right direction indeed. So it means that if you have a theory which is based on some objects, with those objects you're able to compute many different observables in a reliable way. But this is not always the case. Okay, this is not always the case because QCD is somewhat special compared to QED. Why is that? What's the big difference between QED and QCD? There are several differences, but let's say um, if you think about bound states, the bound states of the theory, what's another person? So what's the difference between an electron and a proton? The mass, okay, and yeah, and then okay, which means that the proton has what? As a structure, okay. We don't know if the electron, I mean, as far as we know, the electron is a point-like particle, but okay, so it is not as complex as the proton is. So this means that in order to describe the proton, we need some objects that take care of the internal structure, telling you what's the structure, what's the probability of finding a quark in a proton and a gluon in another proton when the two protons collide, okay? So given the structure of QCD, these distribution functions, these parton distribution functions, they have like a peculiar feature. Do you know what? Do you remember what that is? Can you use perturbation theory to calculate these objects? Can you? Yeah, boys. Can you calculate PDFs with perturbation theory completely? No. Okay. No, because alpha strong is like a weird function compared to the coupling constant of QED. Okay, so at low energy, the coupling constant is very big. So you cannot perform perturbative calculations. So this means that the predictive power of QCD is not as strong as the one of QED, because if you perform perturbative calculations in the low energy regimes, your non-perturbative objects dominate the calculation. And if you don't know the non-perturbative distribution functions very well, you cannot predict reliably observables at different energies or for different processes. So it's true that the PDFs are universal, but if you don't know them very well with good accuracy and good precision, then the predictive power of the formalism is not great. So the question is specifically talking about 3D hadron structure, trying to understand in which kinematic regimes the calculation of the non-perturbative matrix element is more dominated by the non-perturbative contributions, and in which kinematic regimes it's more dominated by perturbation theory. So where do you think it's the predictive power can be the largest? So if I tell you, so in this regime, perturbation theory dominates, and this other kinematic regime, the non-perturbative corrections dominate. In which regime the predictive power is higher? The perturbative one, okay, because we know how to do perturbation theory. And maybe we know the non-perturbative matrix elements, but not to not with infinite precision. So, okay, so I think you got a little bit of the philosophy of what I want to tell you today. And I want you to do some simple calculations in order to convince you that a specific kinematic regime is more dominated by non-perturbative matrix element, and another kinematic regime is more dominated by perturbation theory. So we are going to do this by looking at the evolution equations of the TMD Parton distribution functions. So in order to start, we have to fix some concepts, okay? So the function you have here is the Fourier transform of a TMD distribution function. Okay, so the evolution equations are implemented more easily. Well, actually, they are defined in this Fourier conjugated space. So Bt is a variable which is conjugated to the partonic transverse momentum. Okay, so the evolution, there are 4 evolution equations. Okay, why 4? Okay, well, we'll see that. So the TMDs depend on 2 scales. So you have X, which is the same variable that you have in collinear PDFs, okay, which is the collinear momentum fraction of the quark with respect to the parent hadron. There's the KT or BT, depending on the space you're looking at. And then there are mu and zeta, which are 2, let's say, energy scales or 2 scales. Does anybody know why we have 2 scales and not just one, like in collinear PDFs? So collinear PDFs are just you were told that collinear PDF are these kind of objects, okay? So where you have the light cone momentum fraction, the same variable you have there, and then you have mu, which is the same mu that you have here. These are collinear PDFs. Why the 3D distributions have another scale? Here, yeah. Exactly, so there are 2 kinds of divergences that you can renormalize in these kind of distributions, whereas here you have 1, okay? So 2 different types of divergences, 2 different renormalization scales, basically. Okay, so it's a little bit more complex. So instead of having like a simple evolution equation, you have more evolution equations. So the first one tells you what the evolution of the TMD PDF is with respect to zeta. So when you renormalize these rapidity divergences, you get an evolution with respect to this zeta variable, which is related to the rapidity. And this function d here acts as the anomalous dimension for the evolution, okay? The second equation tells you what's the evolution with respect to mu instead. So when you renormalize these UV ultraviolet divergences, you have an evolution equation with this anomalous dimension gamma f. And then you also have renormalization equations, renormalization group equations for the 2 anomalous dimensions, d and gamma f. Okay, so you have 4 equations in total. Okay, yeah, this is what I was telling you. These are related to rapidity divergences, and the other one to UV divergences. Okay, so mathematically they take care of the divergences. From the physical point of view, what they do is that they allow you to zoom in the structure that the PDF, the TMD PDF is describing. So what happens is that if you, for example, so a TMD PDF tells you that a certain quark has okay, if you think about like a quark which is propagating in the bound state, this has a certain light cone momentum fraction x and transverse momentum with respect to a direction, kt. Okay, so yeah, this is the kt. This is, I mean, this is a very simple picture. So when you turn on the evolution equations, what you do is to zoom in this kind of picture, and you're able to resolve, let's say, further emissions of gluons. Okay, so for example, if you have another, if you resolve by increasing the scales, your resolutions, you can see that, for example, your quark gets a kick, which is induced which is induced by multiple gluon emissions, okay? Okay, so when you zoom in with these equations, you're actually able to resolve further gluon emissions. Okay, so this is what they do from the physical point of view. So please interrupt me anytime, okay? Okay, in the slides you will find some references, and I invite you to check what's in the references to get a better picture of what I'm saying. So now the goal is to solve these evolution equations. It's pretty easy to look at to build the solution just by looking at these 4 equations. The solution can be written like in a very compact form, where you have, so here you have the TMD PDF at some scales mu and zeta, which are the values at which you want to evolve your distribution. And you start from other 2 values, mu0 and zeta0. These are the initial values, okay? So you take the Fourier transform of the TMD PDF at these 2 scales, and you evolve them by 2 factors, basically. So the first one comes from the evolution in mu, and the second one from the evolution in zeta. So the evolution is multiplicative in this B space, okay? So if you know the 2 anomalous dimensions, gamma, f, and d for these evolutions, then you can calculate what the evolved distribution is. Okay. So the good thing is that these 2 anomalous dimensions are calculable in perturbation theory, so they are power series in alpha strong. So in principle, you can sit down, you do your calculation. It takes 1 month, 2 months, 3 months, 5 years, depending on how many loops you wanna put inside of the calculation. But then at the end, you get some answer. Okay, so it's calculable. You can do your evolution, and everybody is happy. But because of the structure of these functions here, in particular of the D anomalous dimension, there are also non-perturbative corrections to this evolution. These are functions that cannot be calculated in perturbation theory. The reason is that alpha strong becomes too large in order for the perturbative calculation to converge. This is not the only non-perturbative correction in the game, because the input TND distribution, so the object that you have here, can be expanded on the basis of the collinear PDFs, okay? And this is calculable in perturbation theory, this coefficient, but you have another function here, which is non-perturbative. So, what you can, if you think about a quark with a specific transverse momentum, okay, say that you have your direction here. This is the direction of motion of your proton. You have a quark with a certain transverse momentum, okay? This process, so this kinematic configuration where you have the quark with a transverse momentum with respect to the parent hadron direction, let's call it P, okay? It's somewhat related to what collinear factorization tells you, in a sense, right? Because if this KT is large, then this transverse momentum can be described by, let's say, an emission of a hard gluon, for example, and the only non-perturbative matrix element that you have is the collinear PDF. So say the physics of the quark having a transverse momentum could be described by, say, alpha and a gluon emission, okay, a gluon emission this way, and here you would have the coupling in your calculation, and say that the scale at which you evaluate the coupling is given by the KT, okay, naively speaking. So what happens is that if the KT is large, so if the gluon gives a hard kick to the quark, then this transverse momentum is perturbative because the alpha strong is small, okay? So the only non-perturbative process is the motion of the quark along this direction, so which is described by the collinear PDF. If the KT is small, instead, so if you have like a soft emission or a collinear emission, what happens? What's the value? What would be the value of alpha strong in that case? If KT is small. Yeah, we cannot, I mean, I don't want you to tell me the number. Would it be big or small? big. Okay, so my perturbation theory would not converge. So in these cases, when the KT is very small, we need some non-perturbative corrections in these equations. And basically this F and P factor here and the G sub K factor are what they do in a nutshell. So that factor here tells me what is the intrinsic transverse momentum distribution. So what is the, let's say, the part of the TMD distribution related to very small KT, okay? And that function here tells me what happens when I emit very soft gluons. Okay, so when the kick is small because the KT is small or because the gluon is soft. So from the physics point of view, I hope I convinced you that in these kind of distributions, looking at the evolution equations, actually, we have things that we can calculate and things that cannot be calculated. So let's go back to, okay, yeah. So these are the two things that in principle need to be fit on to experimental data or calculated with lattice QCD or calculated with models. There are several approaches to this problem, but we cannot get around the fact that we have non-perturbative corrections to 3D hadron structure. So at this point, we can go back to the original question, okay? So when is the predictive power of TMD factorization highest? When is it large? And when is it small? If we think about these corrections, if you think about this structure here, if we know that we have things that we can calculate and things that we cannot calculate and we have to fit to experimental data. If I calculate a cross-section in TMD factorization, so for example, if I calculate the Drellian cross-section as the convolution of two TMD PDFs, so when is the cross-section, when does QCD or TMD factorization have predictive power in this case? It will be when where my cross-section can be calculated in perturbation theory, right? So it would be basically when the green boxes dominated the calculation. So when the red boxes dominate the calculation, instead, my cross-section could be completely, could be very sensitive to the details of the non-perturbative models that I put in there. So I mean, I would be I need to be very, very careful about what I do. So the question is, where do the non-perturbative corrections dominate? So the answer is kind of simple in a sense, because if this is my distribution as a function of x, bt, and yeah, as a function of x and bt, if I calculate a distribution, a TMD distribution, normally I get something like this, okay? So what we do, what we know that is that the non-perturbative corrections are active at large BT after a certain maximum value of BT, which is order of magnitude, let's say 1 inverse GV, okay? So here, this piece of the distribution here, so for BT larger than Bmax, is dominated by, is actually driven by the non-perturbative models, whereas the low BT regime is perturbation theory, is PQCD, whereas this is non-perturbative models. So if I draw another distribution here, and I have f of x bt, I can have, so B max was around here, okay. This is the non-perturbative model, and this is PQCD, okay. So in which case do the non-perturbative corrections dominate? On the right, okay, because in this case, the bulk of the distribution is actually for BT larger than 1. So for the area under the curve here is given by the details of the non-perturbative model. So what's the why am I drawing two different distributions? What's the difference between this and that? It's actually the kinematics. So usually something like this happens at a certain value of x and q. And this happens at, say, let me call it x1, q1, and this happens at x2, q2, okay? So different value of x and different value of q generate different kinds of distributions where the non-perturbative corrections dominate or PQCD dominates. So the goal of today's recitation session is to try to understand what's the hierarchy between these x1, x2, and q1, q2. So what would you expect for these values of x and q, and what would you expect for x2 and q2? Would you expect q here to be small or large? Would you expect x to be small or large? Does anybody have an idea? What, x or q? So you would say large x here, okay, and what about q? Also large, okay. Halfway right. Okay, but there is a nice way actually to understand this. Okay, so this is the exercise. In which kinematic region is the TMD PDF dominated by small or large BT contributions? Or in which kinematic region is the formalist predictive, namely driven by perturbative QCD, and in which region is non-predictive because it's driven by the non-perturbative contributions? So what we can use is the so-called Laplace method or saddle point approximation, which tells you that if you have, so the TMD distributions in momentum space are related to the integral of this curve, okay? We're gonna see that later. But basically, this boils down to understanding where the peak of this distribution is. Okay, so if the peak of the distribution is in the low BT region, it means that the integral will be dominated by PQCD. If the peak is in the large BT region, it will be dominated by non-perturbative corrections. Do you want to say something? No, you were just stretching your arm. Okay, good. All right, so have you ever heard about this method? Yeah, probably yes. Okay, so if you have an integral, a certain integral of this type, which is you have to have a function that does not oscillate too much, f of x, okay, and you integrate the exponential of this function. If you can extend the integration region from minus infinity to plus infinity, then what you can do is to calculate, in order to calculate the integral, instead of calculating the integral itself, you can evaluate the integrand at a certain x0, which is called the saddle point of the integral. So instead of going through the hassle of calculating the integral, you can just take the integrand function and evaluate it at the saddle point plus some factors in front of it. Okay, so what we have to do is to try to understand where the saddle point of the TMD PDF is. So why is that? Because we said that the KT, the distribution in KT space is the Fourier transform of the TMD in BT space. So for the unpolarized PDF, this boils down to an integral of this type, BT KT, and then you have x BT square mu zeta. Let me see if I wrote it. No, okay. So the Fourier transform, if you integrate over the angular parts, includes a J0 function here. Okay, so how does the integrand look like? So this is a regular function like this one. What does the J0, the Bessel J0 function do? Do you remember? Is it an oscillating function or like a monotonic function? What is that? oscillating. So we're not really in the framework where we can apply the saddle point method because the J0 is rapidly oscillating. So what we do is to evaluate this function at kt equals 0. Okay. What happens at J0 if you set the argument equal to 0? Do you remember? So J0 of 0 is equal to 1, luckily, okay? So you get something like that. Okay. So in this case, the integrand is looks like this. Actually, you have to multiply these functions by bt, so the shape will be a little bit different, but it's not an oscillating function anymore. Okay, so our goal is to try to understand where the saddle point of this integrand is in bt space, in order to understand if this function is dominated by a bt value in the small region or in the large region. Okay, so if the saddle point is in the small bt region, then this function will be dominated by perturbation theory. If the bt saddle point is in the large bt region, this will be dominated by non-perturbative contributions. So at this point, I leave it in your hands, okay? So we have to try to, let me see, no, this is not, okay, so this is, if you start by this kind of result here, what you need to do is to understand where the peak of the integrand is. So in order to understand where the peak of the integrand is, you have to calculate the derivative of the integrand and set it to 0, okay? So I would like now to involve you directly in this calculation. And I was thinking of like dividing you like in 3 teams. Paying tribute to QCD, we can have the hard team, the soft team, and the collinear team, okay? There are no overlaps in this game, contrary to the QCD case. So how many people do we have here? 30 more or less? 20? Okay, so please cluster yourself in 3 teams, 7 people for each team, please. And then we see how to tackle this, okay? We can think about the prize for the team. Exactly. First line. 1, 2. One, okay, and 3, okay. So I don't know, number 1, please come here in this corner. Number 2 over there, and number 3 a little bit higher, I would say. And then I ask the organizers to think about a potential prize for the people who get to the answer first. Yeah, take a seat. It's not that you want to do calculation standing, right? That's They are going to do exactly the same calculation. Why? You think so? It is exactly the same calculation. It is, it is. No, yeah, yeah, I said yes, it is. No, 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 no. So we have to get to the same point. Okay, so let's go. Let me finish 1 second here. So we said that in order to apply this Laplace approximation of the integral, you want to go to an integral representation where you integrate from minus infinity to plus infinity rather than from 0 to plus infinity. So one way to do it is to change variable in the integration from bt to the log of bt squared. So you can, if I, okay, then please I would ask you to tell me if I did something wrong, okay? So if you change variable from bt to the log of bt squared, then the integral becomes an integral from minus infinity to plus infinity, and you have, so you integrate in log of bt squared, you have a 4 pi factor, and you have bt squared times f of x bt squared mu and zeta. I'm not really able to draw this letter, so you will see a wiggle. Okay. Okay, so now we have the minus infinity to plus infinity integration, but we have to put it like in an exponential form. You see that over there you have the exponential of a certain function f, whereas here we don't. So we need to have the exponential of something. What can we do? What? Exactly. Pretty, okay, so let me go, let's write it here. So this would be the integral from minus infinity to plus infinity, the log of bt squared 4 pi, and then you exponentiate a log. Okay. At this point, so okay, let me erase this and okay. Okay, so once you put the integral in such a form, in order to find the saddle point, what we need to do is to find the stationary point of the integrand, so the maximum. What do you do to find the maximum of a function? You derive it, okay, and you see where the function, where the derivative is 0, okay? You can find maxima or minima, but okay, so we will have one stationary point here. So what you have to do is to calculate the derivative of the equivalent of the function f, so whatever is inside of the exponential. And you see that it's precisely the equation that you have here. Okay, it's the derivative, actually it's the derivative with respect to the log of bt squared, this variable here, of the log of bt times f. But that's equivalent, since the saddle point will be different from 0, you can show that it's equivalent of calculating the derivative with respect to bt. Okay. All right, so another thing I want you to remember is that for sake of simplicity, we can fix these two scales, mu to q and to q squared, okay, which is, for example, in Drellian, the invariant mass of the intermediate vector boson, or in semi-inclusive DIS, it's the invariant mass of the virtual photon. But okay, just to have one letter less. So this will be xbt q and q squared. Okay, at this point, the exercise begins. So the goal is to calculate, for you to calculate this derivative. Before actually calculating the derivative, I would like to suggest you to calculate this object. Okay. Then you take the derivative, you evaluate this derivative at the saddle point, and you equal the derivative to 0. And you will find that the saddle point will be a function of x and q. So this function of x and q is the solution of this equation, actually. So, and it's going to tell you, as a function of x and q, if this number becomes big or large. So if the predictive power of the formalism is low or high. Okay, so how do you do this? How do you calculate this? What can you do? Since we have to use the evolution equations, we look at what? Yeah, this function here, this form here. Okay. Let's use this. Let's forget about the non-perturbative contributions for a second. Let's look at this function here, this structure here. By using this structure, plug it in here, okay, and see what you can do. See what happens. Okay. All right. So the reason why I suggested you to work together in groups is just to, maybe you can help each other to warm up the brain or give you suggestions. It depends. I mean, some people love to do calculations by their own, like sitting in a corner. Other people get more enthusiastic if they do things together. I belong to the same category, to the second category, and I would suggest you to do the same, to try to do the same. So when I do similar things with my students for the quantum mechanics class in Turin, the first 2 lectures, they stare at me like they hate me. But then I think it pays off, but in the long run. So today we only have 2 hours available, but I think you will like it. I hope so, at least. So there is also a file in the same folder that I shared 2 days ago. There is a file with the solution of this calculation. Okay, so you can also take inspiration from that one if you want. Let me see if it's already there. If I put it in there. Yeah, so it's this file, evolution and predictive power. If you open it, you find the answers to your questions. No, sorry. Okay, it's not in there yet. Okay, now you will find it. Yeah. Okay, but let's get back here. Okay. So we changed from bt to the log of bt squared because we want an integral from minus infinity to plus infinity. That's just a requirement coming from the applicability of the Laplace method.
But this change also depends on F because you have to change bt with log of bt and then redefine a new F of bt.
No. I mean, it's just a change of variable in the integrand, but it doesn't affect the TMD PDF itself. You just get the bt square factor instead of bt in front of the PDF. Okay. Okay, so I don't think so. You can start from let me get the pointer. You can start from this equation here. So from this one, and just plug this formula here. So what you need to do is to find an equation by starting from this one. You need to find an equation that involves gamma f and d. Okay. it will include the f at the initial scale, gamma f and d. And it's just a matter of multiplying bt squared by this and taking the log. What is the log of, if you have a log of a times b times c times d, or log of a times b? It's the sum of the logs. So something similar will happen here. Okay. So I think it is instructive to see this calculation at least once. Maybe in a school it's the right place to do it. What's the time? Okay. Yes. Exactly. It depends on the product of bt and mu0, yeah. So but one could write the d as a function of bt and alpha s. You find actually different conventions. Okay, so let's see. Yeah, you have the log of bt squared and the log of this function here. Exactly. And then you will have, so the function f is also the product of three factors, right? So eventually you will have like the sum of a few logs. Yes. Say it again. Hmm? No, but at this point, don't take the derivative yet. So just calculate the log. Just calculate the log. And before taking the derivative, we have to make some other assumptions. Are you already taking the derivative? Okay, no. Okay. Okay. I mean, you can go straight ahead and calculate the derivative, but you will face some problems in the sense that you don't know what gamma f and d are. Okay, so we have to, yeah. So how do you derive a function that you don't know? You have to, oops. So the way we do it, so the way we proceed is to evaluate gamma f and d at the lowest order in perturbation theory, which is the order at which you can do calculations analytically. If you assume to operate at the lowest order, the calculation boils down to a quite simple thing. But if you don't, then it becomes more complicated and it can be solved only numerically. Okay, so tell me now. Okay, so let's parenthesis missing. Do we have one volunteer to specify what this log is? So volunteer number 1, Luca. Okay. Okay, the log of bt squared times f. How do we split it in different terms? Okay, so that's the log of bt squared. Yeah, okay. Okay. Mm-hmm. Okay.
And then the last term is just if you apply the log n, you can put it outside and you have minus.
Yeah. Okay, very good. Are we on the same page? So you have the log of a product of, you have 4 terms in the products, bt square, and then line 1, line 2, line 3, and it becomes the sum of these 4 logs. Okay, so in order, thank you. In order to move forward, we have to make some assumptions. So as I said, gamma, f, and d, these are objects that can be calculated in perturbation theory. So in the notes that you can find online, you see their expression, at least the general one. So let me see. Okay. So gamma f, just, gamma f, the anomalous dimension for the evolution in mu, is the sum of 2 things. It's minus the gamma cusp anomalous dimension. Okay, and then you have a log zeta divided by mu square. And then you have another term which is called the non-cusp anomalous dimension. Okay. So these 2 objects here, these are power series in alpha strong. So it means that alpha, so let me, so this gamma cusp, you know it better than what I do probably. So it's a sum of these coefficients. So these are just numbers, gamma. And then you have a power of alpha s divided by 4 pi. Okay. So to take the lowest order, we just calculate, we just take n equal 1. So what we have, we truncate these two, gamma 0, alpha s divided by 4 pi. So if you do the calculation in perturbation theory, it happens that gamma 0 is 4 times CF, where CF is the Casimir factor, and it's equal to the number of this is the number of colors minus 1 divided by twice, yeah, the number of colors. So this becomes basically CF alpha strong divided by pi. Okay. So in general, what happens is that in order to understand how to combine this term and that term, you have to assume some hierarchy between the coupling constant and this log, which can be large as well. So usually there are several ways of doing this, but usually if you have alpha strong times the log, this should be like order 1. So the counting is done in such a way that alpha times log is 1. So if you want to take the leading contribution of this anomalous dimension, that the gamma cusp contributes at one order in alpha, which is higher with respect to this. So if you take the leading order term of gamma cusp, you have alpha strong times the log. Alpha times the log is 1. So you don't take any contributions from the non-cusp anomalous dimension because it would contribute to order alpha only. So long story short, gamma f, what we need for gamma f is the following. Is basically it's minus CF alpha strong over pi times the log of zeta divided by mu square. Okay. And let me see, yes. Okay, so this is the expression, this is the so-called leading log approximation. Okay, so this is the leading log approximation. Gamma f is given by alpha times a log, which is order 1, so it's leading. Okay. Then we need to know about d. D is another function like that one, but it's a little bit more complicated. But at the leading log, it boils down to something simple. So d is, in general, so let me see if I remember it correctly. So let's write down immediately the leading log approximation, which is simpler. This becomes twice, this is mu, sorry, bt mu alpha s of mu. At the leading log, this is 2 times CF alpha strong pi log of mu squared divided by this quantity mu b squared, where mu b is defined as 2 times e to the minus Euler gamma divided by bt. Okay, let's call it, we don't really care about this value. Let's call it C0. It's roughly equal to 1, by the way. Okay, so this is the function that we need for d, and that's the function that we need for gamma f. Oh, yes. Yeah, so what was the question? Yeah, this is the, this is the leading term of the expansion for d. True, true, but it's not the complete story, so you will see that in a second. Okay, okay, so does d depend on bt through this variable here? As you were saying, so gamma f does not depend on bt, so why do I care? That's a good point, but like, be patient for a second. Okay, so these are the leading log contributions. So inside this function here, we will use the leading log approximation, and for this function here, we will use the leading log approximation. Another important thing before moving forward with the calculation is the following. So several times when you perform these perturbative calculations, you certainly know better than what I do. Before calculating, it's good to stop and ask yourself if you can make some sensible choices in order to make your life simpler, okay? So especially, life is simpler when you don't have logs spoiling your morning or afternoon. So let's look at d, at the d function. What's the choice for the scale mu that simplifies your life most? If you fix mu equal to mu b, then the log is 0 because you have the log of 1. Okay, so the good thing to do is to set the initial scale in this calculation mu 0 equal to mu b, so that at the leading log this function here is 0. So in the calculation over there, I invite you to use mu0 equal to mu b, okay? And also that zeta 0 will be mu b squared, okay? So zeta 0 is, this is, I mean, the dimension here is GV, this is GV squared. So we fix them at the same value, but this has to be the square of mu b, okay? So if you take mu0 equal to mu b, sorry, this becomes simpler because this goes to 0, okay? So in a nutshell, what I'm asking you to do is to go ahead with that equation using the leading log approximation and mu0 equal to mu b, okay? So that we have less logs to worry about. Let's now go ahead. Okay, so you have to basically, so this is 0, we only have to worry about this gamma f. So why, so you were asking, okay, we don't care about gamma f because but mu0 now is mu b. Okay, so at this point, this integral is a function of b, is a function of bt. Okay, so that's the trade-off. I mean, this is 0, but this becomes a function of bt. Okay, so when you take the derivative, you have to take that into account. So let's put this is mu b squared, mu b, okay. And also we fix, so zeta 0 is mu b squared, and mu square equals zeta equal q squared. So the final scales, let's call them q and q square. So this was the initial. Mu here is q, okay. This is q square. And here you would have basically q square divided by mu b squared, but we don't really care too much because it's multiplied by 0. Okay, let's go ahead. Yes. Yeah. No, that would be the log of q squared divided by mu b squared. So because yeah, in that log you have so no, sorry. So this is integrated over that mu square. The pointer. Oops. Sorry, I was pressing the wrong button probably. Okay. Now, so over there, okay. So alpha times log, I mean, when the log is non-zero, of course, alpha times log is supposed to be order 1 because these logs are large and alpha is small. So the product should be around 1. So in our case, mu is integrated over because you see you have the integral over mu. So it's not that mu is equal to q and square. This is equal to q square and this is equal to q square. Yeah, exactly. That's mu prime. Mm? Just plug the expression of gamma f at the leading log and see what happens. Then I didn't tell you another thing, but I'm waiting for you to ask. Yes? Say it again? Yeah? Alpha strong, you can leave it as it is for the moment, okay? But at some point we have to understand what alpha strong is, so that's gonna be another story. So at this point, just plug gamma f and let's see what happens. So we said that we can forget about this, right? We can forget about this, and our gamma f. Let me write it here. So this is over there. So let me write minus CF over pi. Then you have alpha strong of mu prime times the log of q squared divided by mu prime squared. Yeah. Do we all agree? Does everybody agree? Okay. So um, can you remember your name? Can you remember me your name? What's your name again? Angel. Okay. So Angel was saying, in order to calculate this integral, we need to know what alpha strong is. That's right. But what we need to worry about is not really calculating the integral, but taking the derivative. Okay. So what we need to do is to calculate this derivative. Let's call it the derivative of log bt square of this function and put it equal to 0. You evaluate this derivative at bt equal to the saddle point value, btsp, and put it equal to 0. Okay, so let's now worry about that. So this is our function, and we derive it. So my claim is that you don't really need to know the shape of alpha strong in order to take this derivative, right? So you derive with respect to the log of bt square, and mu, keep in mind that mu b is a function of bt. So you have to take a derivative with respect to bt, and the one of the integration limits is a function of bt. So you don't really need to calculate the integral, but you can use calculus 1 to evaluate that derivative. Yeah? Yeah, but yeah, okay, but that doesn't really. Yeah, it's the same. But in principle, you're right, but for the sake, okay, at this level, it doesn't change the shape of the TMD PDF, okay? You can derive with respect to the log of, you can derive with respect to BT instead of the log of BT square. Then that's the same thing. So the very first term is super easy. What's the derivative of the log of BT square? 1. Okay, you derive with respect to the log of BT square, log of BT square. So you're gonna get 1. Okay, and then something else. So, okay, now at this point, I think it's good to introduce, to tell you something else. So we said we evaluate D at the leading log with mu B, and this is equal to 0. We evaluated gamma F at the leading log, and F of X BT square mu B square. We said it's so if you're looking at a specific flavor I, okay, so this expression here in perturbation theory is the sum over all the other flavors and the gluon, and then you have some coefficients Cij, okay, convoluted with the these are a function of x, bt, mu b, and then it's convoluted with the collinear PDF of the flavor j. Okay, this is the generic expression. So if you evaluate it at leading log, okay, this is a delta on the flavors. It's delta ij. Okay, so this function here contains all the collinear splittings of quark and gluons. But if you do the leading log approximation, it means that you're not including any power of alpha strong in this C coefficient. So it's just a delta on the flavor indices. And what do you get if you sum over the flavors of delta ij times the collinear PDF? What do you get? So this is the PDF for the flavor j. You have delta ij and you're summing over j. What do you get? It's just the flavor I. It's just a collinear PDF with flavor I. Okay. So at leading log, this is just a collinear PDF as a function of x and mu b. This is just to tell you that there is a simpler expression. So then we can go ahead and calculate the second term, right? So the second term will be the derivative of log with respect to log bt square of the log of f1 collinear. And then you have to derive this term here, the third term, which is the tricky one in a sense. We are almost done, eh? How's it going? I see smoke coming from the ears. No. Yeah, that's right. So, but and then what happens if you so we have to derive an integral. We have to derive an integral, and the variable is inside one of the integration limits. Hmm? Exactly. Yeah. 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 So the upper limit does not depend on bt. The lower limit does. So that derivative will be contributed by two terms, the difference of two terms, but the first term is zero because q does not depend on bt, and then you're left with the second term only. Yeah. Let me see. So that's correct. So this is yeah, this is complicated to this. Okay, so this derivative will be proportional to the Diglap splitting kernels. Okay, but I mean that has to be calculated numerically. So we okay, we will leave it as it is basically. Okay. Um, then you have, I mean, we can, once we get to this point, we have to manipulate a little bit more the equation. So what do we need at this point? What do you think we need? Exactly. Okay. So alpha s, which scale? Okay, mu b, exactly. Yeah, 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 yeah. Oops. Daniel, do you wanna tell us what the derivative of the third term is? Yeah, yeah. I mean, it's fine. Everybody makes mistakes. There's no shame on. Yes. Exactly. Yeah. Okay. Yeah, exactly. It's the third minus sign. Okay. Yeah, that gets simplified. So and then everything is equal to zero. Exactly. So we need to. This is the derivative. We set the derivative equal to zero, and we evaluate that this expression for bt equal to the saddle point. So let me call it. Let me put another chalk. So let's call this mu b star. Okay, star star, and that's it. Where mu b star is C0 divided by the saddle point. So it's basically mu b, but with the saddle point value replacing the denominator. Okay, thank you. So we have one, the derivative of the log of the collinear PDF, and then we have something that depends on the coupling constant and the log of q squared divided by mu b squared. Okay, so what's next? I mean, we need to find, as I remind you that we need to find an expression for the saddle point as a function of x and q. Okay, so the dependence on bt sits inside of the log, sits inside of the alpha strong and the collinear PDF. So we need to invert this equation in order to see how we can write bt, saddle point, as a function of x and q squared. So the x dependence will come from here, and the q dependence will come from here. Okay. Do we know everything in this equation? In order, do you know everything in order to calculate bt as a function of x and q? Can we just sit down and invert this equation and derive bt as a function of x and q? Or do we miss something? Are we missing something? We need alpha s, okay? So we need to know what the expression of alpha strong is. And in principle, we also need to know, let's say, how to calculate the bt dependence from this function here. So this is the most tricky thing to do. And for now, what we do is to operate assuming that we neglect this function. Okay, so let's call this function capital X. This is a function of x and how do I call it? X and mu. Okay. So for now, in order to simplify the calculation, we set this equal to 0. Okay. So setting this equal to 0, what do we lose? Which kind of information are we losing? We completely lose the x dependence. So we have to, at this point, if we assume capital X to be 0, what we're going to find is a dependence on the q variable for our saddle point. So we are losing something important, okay? But it's the only way to get a simple solution. Okay, let's see what happens. Okay, so capital X is 0, and what about alpha strong? How do we know alpha strong? What can we do? Well, so there are people who sit down and calculated alpha strong to 5 loops, but of course, we're not going to use that because it's too complicated. So alpha strong is a solution of a first order differential equation of this kind, okay? It's you have it everything is in the notes, huh? So you have okay, of course, yeah. So if you have alpha s, so the logarithmic derivative of the coupling, the derivative of the coupling with respect to the log of mu squared is equal to the beta function. Okay, so this is the function that people calculated up to 5 loops, if I remember correctly. So it's a power series in alpha, and the leading term is alpha squared. Okay. Then you have things which are smaller than alpha squared. So if you truncate the beta function to the leading term, we can actually solve this analytically. Okay. You can separate the variables and find the solution for alpha strong as a function of mu. And then we use this expression in our equation there. Okay. So how would you do it? I already told you how to do it, but yeah, please do it. What would you get? Oops. So this coefficient here in QCD is equal to 11 times CA minus 2 times the number of flavors divided by 12 pi. So CA is equal to the number of colors in QCD, and this is the number of flavors. So the number of active flavors. So in principle, the number of active flavors depends on the energy scale. Can be something that depends on the energy scale. It depends on the framework that you use. But so in principle, this could be a function of mu as well. But in our case, we keep it fixed. Okay, it's just a number to make things simple. So B0 is just a number here. So if you sit down and you solve this differential equation, what would you get? What's the time, by the way? Okay. I mean, we didn't take a break, but maybe we can finish a few minutes earlier. Exactly. So, but you lack a constant. So you take an indefinite integral. Yeah. Okay. And then you fix it somehow in order to have a like a, but okay, we'll see. Why don't you tell us? So if you separate the variables, or how would you tell me how would you do it? This is, of course, not the way you do things if you want to do precision physics. Okay, if you want to do precision physics, you have to take into account all the higher loops in the beta function. But it's gonna give us the correct behavior qualitatively. No, but you can just integrate, calculate the primitive function. That's yeah. Okay, exactly. You can just calculate the indefinite integral without setting limits on the. I mean, I don't know how would you do it. For example, if you have a different way of doing that. Exactly. Yeah. But that's not 1 over alpha s squared. It's exactly 1 over alpha s. Okay. So the coupling. Then I mean this c factor here is arbitrary, right? So you can set it, for example, equal to in such a way that you fix the initial value of the energy scale in the second step. Exactly b0 times the log of mu 0. Exactly, but it's mu, I think it's mu squared and mu 0 squared. Okay, so yeah. So I think it's okay. If you have a plus sign here, I think this is a plus as well, right? Yeah. So okay, if you put a minus sign here, I think it's correct. So that alpha s is basic. Okay, go ahead. Do you agree with me that it's mu squared divided by mu 0 squared if you keep the minus sign? Okay. Uh, yeah, but it's 1 over, right? So what I get is alpha s. I get like b0 log of mu square mu 0 squared to power minus 1. So the inverse of this. Yeah. Yeah. Exactly. Exactly. So for example, thank you. So this can be, for example, your lambda QCD parameter, okay? Okay, thank you. So this, in our case, will be lambda. Let's fix it to lambda QCD, okay? So this is our simple expression for the alpha strong, yes. Yeah. Yeah, I mean, you can choose whatever initial condition. Yeah. So here we fixed the C constant in such a way to be equal to minus the log of lambda QCD. But you can do it with other integration limits, for example. But okay, so okay, now that we know alpha S, let's plug it in here. So let's go back to our equation. Okay, we go back to our equation, which was 1. Okay. So what we had was 1. We are neglecting x, and then we have minus CF over pi, 2 pi, mu b, sorry, no, alpha strong mu b star, okay? And then we have the log of q squared divided by mu b star, okay, equal to 0. So now if you plug alpha strong in here, we can actually invert, we can find BT saddle point as a function of q squared. So this is the last step that we have to take care of before finding a solution. There's a little bit of algebra with the logs, but it should be okay. So once again, what we need to do is to take the derive of something which is BT saddle point as a function of Q, okay, from that equation. So you have to invert and solve for BT. We're very close, aren't you excited? I don't see the excitement. Oh, actually I can. So this looks like a simplistic calculation, but it's actually what you can find in the original paper by Parisi and Petronzio, the 1979 papers, and the paper by Collins Opera Sturman in 1985. They did exactly the same thing, but at the level of the cross-section. So we are repeating this at the level of the single TMD distribution. The mathematical structure is the same. Yeah, it's in the right direction. You have to solve for BT, which is so exactly. You have to solve for this variable. You have to invert the equation for and solve for BT as P. Yeah, exactly. What's the time, please? Okay, thanks. Let's take a few more minutes and then we see what the result is. So I have an idea about the price. I think Alessandro can get you a copy of the original paper by Collins, the 1995 paper signed in person by Collins, right? If you get the result right. We get to see him every once in a while. True, 7, yeah. Yeah, but we don't see him in our in the conferences in our community. Have you ever met John Collins in person? He's a friendly person, so you can talk to him about TMDs and. But he's more friendly, yeah. I think, yeah. Maybe I should turn off the microphone. It's as friendly as the red book is. Okay, so let's see. Okay, now we're getting to, yeah, so you're close. Yeah, exactly. But you have to solve for BT. So this is mu b, which is the C0 constant divided by BT. So you're almost there. Let's see how it's going. Okay. You're done? No, okay. Okay. So if you do a little algebra and you manipulate these logs and the logs that is inside alpha strong, the log which is in here, and the end of the day, you have it? Let's see. Yeah, but then you have to solve for BT. Yeah. Yeah, I told you, I mean, it's a little bit cumbersome, but eventually you will get there. But let me tell you what the result is. So at the end of the day, so if you solve this equation for BT, in particular BT saddle point, you get a function of Q only, which is C0 divided by lambda QCD, or the initial scale that you chose to solve the RG equation for the coupling. And then you have the ratio between Q and lambda to the power gamma 0, the ratio between gamma 0 and gamma 0 plus 8 pi b0. So gamma 0 was just 4 times CF, okay? So it's a positive number. And b0 was the coefficient that we put over there. But basically, so the exponent is a positive number. So this function, what does this function tell you? So the Q dependence is in here. So The original question was, we have to understand if when BT saddle point, so when the peak of the function in BT space is in the small b region or in the large b region. Okay, so this function tells you what happens as a function of Q. So if Q is small, what happens to BT? It increases, right? So at small q, BT is large, and at large q, BT is small. BT saddle point is small. So that means that what you said in the beginning was correct with respect to Q. So if you are calculating, let's say, Z boson production, so if Q is around 91 GeV, your TMDs will be peaked in the low BT region, and the calculation will be dominated by the green boxes here, perturbation theory. Okay. Whereas if you're calculating semi-inclusive DIS at JLab, where Q is around 3 GeV, then the saddle point will be in the large BT region. So it means that your TMDs and the cross-section will be actually dominated by non-perturbative corrections. So this tells you two things. That first of all, you have to know the non-perturbative functions pretty well in order to calculate cross-sections reliably. And the second thing it tells you is that at low Q, the experimental data that you get at a low Q are, say, more interesting to extract non-perturbative information because the cross-section that you calculate is much more sensitive to those functions. Okay, so if you fit data at low Q, there are several problems, but the good thing is that those data are very informative about the details of the models that you put in your cross-section. Okay, so we forgot something, didn't we? We said that this function, we set this function equal to 0. So if this function is not equal to 0, and if you repeat the calculation, what you get is a correction to this form. You get an x dependence as well. And here you just have to multiply this denominator by 1 minus this capital X. So the problem of this equation, so you get the capital X function in the denominator of the exponent. The problem is that the function itself depends on BT, so you have to solve it recursively. Okay, so that's why it's a bit more complicated, and it's also difficult to get an intuition of what happens as a function of X just by looking at this equation, because this is the derivative of the logarithmic derivative with respect to the coupling, actually. But so one can sit down and see what happens. And if you, let me see. Okay. Okay. So here is what happens as a function of X and Q. So let's look at the purple line. So the purple line is the leading log solution, the one we calculated for the saddle point as a function of X and Q. So the orange line is the position of the saddle point without the X dependence. So you see it's a constant. If you include this function here, you get the purple line at leading log, which tells you that as a function of X, the predictive power decreases because the TMDs have the saddle point in the large BT region. Okay, so if you go towards large X, at some point your saddle point is going to be at a BT which is larger than 1. So it's dominated by the structure of the non-perturbative functions. So it's the opposite of what you said. So the predictive power is maximum at large Q and small x. Whereas if you go at low Q, and here Q is fixed, but if you go towards large X, so the saddle point goes in the large BT region. Okay. So again, JLab physics, low Q and large X. Okay. So JLab physics is very, very, very or semi-inclusive DIS at low energies. So fixed target experiments like Hermes, Compass, JLab, There are tons of problems related to the applicability of the factorization framework, but from the point of view of having the data, having informative data about non-perturbative physics, it's the best. Actually, it's good. The best would be kinematic regions where the, let's say, the applicability of factorization is under control, so Q is large, but then you have anyway data at large X. So, for example, RIC data, or if you build, if you build like a fixed target experiment at the LHC, you know that there is this proposal to build to put a fixed target inside of the LHCb experiment in order to have fixed target collisions inside of the LHCb in the LHCb experiment. That would be very interesting, I think, because you can do, for example, Drellian physics, or you can measure other processes as well, where Q is relatively large, so your factorization applicability is safe, but then you can have events also in the very large X region because it's a very forward experiment. So you would have data which can tell you something about non-perturbative physics. So what are the dots instead? The dots is exactly the same thing that we did, but using a higher orders in perturbation theory. So it's the next to leading log calculation. So 2 orders higher with respect to what we did. You see that, okay, the values are different. So you have dots and not a line because you have to solve it. You have to solve these kind of equations numerically. So it's not this solution anymore, but you start from the very same, you start from this. You solve it numerically. And you still get, so the values are different, but the trend is the same. So the leading log solution, the analytical solution, captures this behavior pretty well, okay? Okay, I hope you like it. You liked it. I think it's an informative exercise, and if you, okay, so if you can take home something from this exercise, I'm actually happy. The second thing I wanted you to have a look is to try to implement the solution of these evolution equations and see what happens to a TMD distributions when you increase the energy scale. But I think we don't have enough time. I would leave it as an exercise for, not for the weekend, because the city is too nice to sit down and do exercises, okay? So in the future, whenever you want to have a look at it, please do. And if you have questions, you can feel free to ask, okay? The material is online. Okay, we are done.